Hello students, welcome to our review of graphing linear functions. Now before I get too far into how to graph linear functions, I wanted to talk for a moment about why we graph linear functions. And when I was in 8th grade, my algebra teacher started teaching me this, and I didn't quite grasp why all of a sudden the equations needed to turn into graphs. So I'd like to present with a problem. I'm thinking of two numbers, x and y. And one important fact about x and y is that if you add them together, x plus y is equal to 10. Now go ahead and think about it for a moment. Do you think that you can pick out the two numbers that I'm thinking of, x and y, that add up to 10? Now you might have some guesses, but you can't really say with confidence what two numbers I'm thinking of, because it's possible that x could be 1 and y could be 9. But it's also possible that x could be 9 and y could be 1. Or it could be x is 2 and 8, or 8 and 2, or 5 and 5, or 3 and 7. Or if we want to get even more tricky about it, we could say, oh, well, what if it's 9.9 and 0.1? Or what if it's negative 30 and positive 40? And how long could we keep doing this? Literally infinitely. We could sit here for the rest of our lives, our children's lives, and our grandchildren's lives, just thinking of numbers that add up to 10. But if I asked you to tell me all of them, I need to know all of the numbers where x plus y equals 10. Now, this is where René Descartes comes in with his Cartesian plane. And normally we have a number line that looks like this, and this is great for one variable. So if I want to talk about the variable x, I can say x is 0, or I can say x is 5, or x is negative 13, like this. But René Descartes came up with the Cartesian plane, which was basically the x-axis here for one variable, and then another number line on top of it right here that we called the y-axis. And that let us compare the values of two different variables. So let's go ahead and see what that looks like. I'm going to put one in here. This is a pasted one, that way we can have some accuracy with our squares. And just start thinking about x and y. I'm going to change colors here so it'll show up on the white graph. We've got x and y such that x plus y equals 10. If I start off with the easiest one, I could have if x is 0, y is 10. And that right here, if I go to 0 on the x-axis and 10 on the y-axis, I get that point right there. That represents when x is 0, y is 10. Well, what if I switched them? When x is 10, y is 0. So if x is 10, y is 0, we'd go right there. Well, what about, I think the first one everyone thinks of is 5 and 5. When x is 5, y is 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And when x is 3, y would be 7. So when x is 3, y is 7. And when x is 7, y is 3. Be right here. What about throwing in some decimals then? If x is 3.3, then y would have to be 6.7. So if I went here, 1, 2, 3, and a little bit, would be 1, 2, 3, 4, 5, 6.7 would be right there. Now, like we said before, we could do this literally infinitely. We could go on forever doing this. But if I look at the graph right here, I'm noticing that these points follow a specific pattern. And so what I can do is, instead of spending the rest of my life thinking of numbers that add up to 10, I can say I see the pattern, and any number that lands on this line right here is going to add up to 10. So the big point of all this is that if I have an equation that has two different variables, it has an infinite number of solutions. and we draw lines in order to express all infinity solutions. Now, with that being said, let's go into our first form of graphing. First form of graphing that we have is called slope-intercept form. Now, the word slope right here is used to represent the amount of change, where the intercept is specifically talking about the y-intercept, where it crosses the y-axis, but I like to think of that more as a starting point. This is when the input equals 0, which is usually where most real-world applications start. So, slope-intercept form is y is equal to mx plus b. I'm going to put some labels on this. X in any function will be our input, where y will be our output. The m in this equation stands for slope, while the b in this equation stands for the y-intercept. And when we graph in this form, our slope is going to be the rise over the run, or the change in y divided by the change in x. The y-intercept will be our starting point, which will be located at x is 0, and then y is whatever b is. Now, that's a lot of information all at once, but this is actually a very, very simple form to use. So let's go ahead and graph some functions with it. Let's try graphing y is equal to 2/3 x plus 1. Stick a graph in here. Okay, so I'm going to write that right next to the slope-intercept form equation. Y equals mx plus b. So from here, I can see that the slope is 2/3, while the y-intercept is 1. So since the y-intercept is the starting point, I'm going to make a mark right here to say that I am going to start always 0 and then b. Going to start at the point 0, 1. 0, 1 is this point right here. Now that I know that, I can take my slope, which I know is rise over run, and that's going to turn into go up 2 and right 3 from my starting point. From my starting point, I'm going to go up 1, 2, and then I'm going to go right 1, 2, 3, and then that's where I'm going to get my next point. And then again, just to make sure I've got a straight line, I'm going to go up 2 and right 3, and that'll be my next point. If you're feeling a little unsure, you can also go in the opposite direction. So instead of going up 2 and right 3, I could also go down 2 and left 3, which gives me another point. Now that I have those, again, I can do this infinitely, but instead of that, I can say I can now see the pattern. And so I can connect these dots here, and I've now expressed all infinity solutions with a straight line. Let's do one more example of this. Let's talk about y is equal to negative 3x plus 7. Let's get our graph ready. Okay, so in this one, again, I'm going to put the slope-intercept form right up here, y equals mx plus b. And then if I look at this, I see that my slope in this case is negative 3, and my y-intercept is 7. Starting at my y-intercept, I'm going to plot the point 0, 7. 1, 2, 3, 4, 5, 6, 7. That is going to be my starting point. From that point right there, I'm going to use the slope. And here's where this is a little tricky, because this is rise over run, but I have an integer here, a whole number. So how do I make -3 into a fraction so I can match it up? Anytime I have an integer like -3, I just put a 1 in the denominator, and that makes it the fraction. Now another question here is, this one has a negative on it, so if I had to move the negative, I now have a fraction with a numerator and a denominator. Does the negative go in the numerator, or does it go in the denominator? The answer is either. I can put it in the numerator or the denominator, but I can't put it in both, because putting a negative in the numerator and the denominator would cancel out, which would make it a positive. So in this case, I'm going to choose to put the negative in the numerator. So if I have a rise of -3, that means it's going to go up -3, or a simpler way of saying that is my line will go down 3. My run is +1, so that means it's going to go to the right. So from my starting point, I'm going to go down 1, 2, 3, and right 1. And there's my next point. Let's do that again. Down 1, 2, 3, right 1. There's my next point. And right now I see 3 points. They're all going in a straight line. So I'm comfortable right now saying that I see the pattern. I'm going to put arrows on the end to show that it goes on forever in both directions. And now I can graph in slope-intercept form.